One use of a surface integral is to compute the flux or the flow of a vector field across some sort of permeable surface. So imagine I have a surface like this, and it's like a net or something, and fluid could kind of flow through it. And I have some sort of vector field that represents some sort of fluid flow. So imagine this in 3 dimensions, and my vector field is flowing through the surface. Then I might want to quantify how much, for example, mass per unit of time is passing across the permeable surface overall. Like if the vector field F represented that mass per unit time, like of a river flowing through a net or something like that. Well, the issue is that the vectors of the vector field might not be perpendicular to the net, and their orientation sort of may vary as you go across the surface. So like over here, maybe the flow of the vector field is almost like parallel to the net itself, so not much of the field is going to pass across the surface at any given time. But when you come over here, you can see that since the surface is sort of curved around, more of the vector field is sort of flowing from one side to another. And you can quantify sort of precisely how much of the field is running across the surface at any given point by drawing a little unit normal and then taking a dot product with the vector field there with the normal. That will extract the component of the vector field in the direction of the normal. So at any point on the surface, we know we can compute a unit normal by looking at, like let's say if we have a parameterization RUV, we could look at a cross product producing a normal vector, and then the dot product between the vector field and the unit normal, which becomes its own vector field, describing what it means to be perpendicular at any point to the surface. This will extract the flux or the flow of the vector field across the surface. So if I've drawn a surface like this, it's just sort of like a sheet, and the vector field is flowing sort of from below to above. Depending on how I systematically choose those normals, I'm either quantifying how much of the vector field flows from below to above or from above to below. And there's sort of exactly 2 choices, right? I can have all the unit normals sticking up, or I can have them all sticking down. So N is a vector field that is a bunch of normal vectors to the surface pointing in one direction, either to one side or to the other. And this brings up a kind of issue with surfaces. Some surfaces have a well-defined right side and left side, or upside and downside. They have exactly 2 sides. So, for example, this like plane looking thing, or many of the other surfaces, like imagine like a paraboloid. A paraboloid has an above and a below, right? And you could choose a parameterization that would produce a normal that shoots up, or you could, find a way to have normals pointing down. And then there are other surfaces which are pretty good for our purposes, like closed surfaces. So take a sphere, the surface of a sphere. A sphere has exactly 2 sides as well, because it's got the side that points out and the side that points in. So you could imagine attaching to every point of a sphere a normal that sticks outward, or you could imagine to every point on the surface of the sphere attaching a normal that points inward towards the center, right? Just another so-called closed surface that sort of encloses some volume of space. A torus is a nice surface for our purposes as well. There's a distinct outside. You could attach normals that point to the outside of the donut, or you could attach normals that point inside the donut. However, there are some annoying surfaces that don't have 2 sides to them. So let me start with sort of the most famous example. This is called a Mobius band, or Mobius strip. And I think the best way to get an idea of what it looks like is to sort of construct it from a rectangle. So imagine you had a long, thin band like this. So it's just a rectangle. That definitely has a front side and a back side, right? But what if you took one end of this and twisted it? So it would result in something that looks like this. Okay, so you introduce a twist in the strip. So this side is still facing me, but you twist it, and then the back side comes to the front, like that. Then what we're going to want to do is we're going to want to glue together this side with that side and create a surface. Okay, so the issue is the following. So I've got my red side and I've got the blue side, which used to be two really separate sides of the surface. But when I construct a surface in this way, what happens is that the place where the blue meets the red links up the sides of the surface. Okay, so if you can follow this, what I did was I took this twisted band with the front side red and back side blue, and I took this part and glued it to that part, which became this seam right here, like that. There's the gluing point. And like I said, the red and blue sides are no longer distinguishable. They're kind of connected to each other. If you trace your finger, let's say on the outside of the band here, you're in the blue territory, and you come back around, you're in the blue territory. But once you get to that boundary, you're suddenly on the red and behind there. And then it comes around to the front again, and you're in the red territory, and you trace the inside at red, and then you come back to this boundary again, and you hit the blue side, flipping behind and hitting, So the two sides of this strip have suddenly become one. And if you can imagine trying to come up with some consistent way of attaching normal vectors, you run into trouble. So if you're attaching normals that you want to kind of point outside, to the outside of the strip, then you're on the blue side to start, and you're attaching these normal vectors pointing outside. And then once you get to the flip here, your vectors start pointing to the inside, like this. And so you aren't really establishing one side at all, because there's no way that you can go around and attach normal vectors that just point to one side. If you're to kind of attach a continuously varying vector field of normals, it sort of hooks up with itself and ends up pointing to both sides at once. That's because there really is only one side to the Mobius strip. Okay, and we don't like this because if a surface is somehow one-sided, then you can't talk about flowing from one side to the other because there is no other side. And there's a really interesting topological object called the Klein model, which is sort of a dimension up version of this, in that this image that's drawn here is not really in 3 dimensions. This is only embeddable in 4 dimensions, but it is a non-orientable surface in 4 dimensions. And the idea is that you want to kind of attach normals that are pointing either outward or inward, kind of like the sphere or the torus. But as you try and do that, the surface wraps around on itself, much like the Mobius band, and your arrows sort of end up at the end pointing in both directions. So anyway, these are just sort of neat objects. And in Calc 3, we are just going to restrict our attention to orientable surfaces. So surfaces that you can attach a continuous normal vector field that either points to one side or the other. There are definitely 2 sides to these orientable surfaces. And, attaching this normal vector is important for quantifying, as I sort of set up here, flow of a vector field across that surface. So flow of a vector field into a sphere or out of the sphere, for example. Okay, you can thank Professor Jason Parsley for this question down here. I've been using his notes this semester, and I encountered this hilarious joke. Why did the chicken cross the Mobius band? To get to the same side. So if you'd like, please email him and thank him for this wonderful joke. All right, now on to quantifying flow of a vector field across an oriented surface. So once I've sort of decided what one side and the other side means to my surface, I might have a vector field that sort of has an amount of flow in that direction. So I'm going to create a surface integral that quantifies that. So the surface integrals that we were creating earlier in these notes allowed for any multivariate function here in the integrand, and as promised, those integrands are going to be constructed from fields in certain ways. So this one that I'm constructing here quantifies flow of the vector field. So if you put that flux or flow into the integrand and you integrate a surface integral over a parameterized surface, you're going to get sort of the total flux of that field across S in the direction that's specified by the parameterization. Now I want to mention something about constructing this integrand because it's a little bit awkward to go right at this formulation. If we make an observation about what this ends up looking like, we can have a little bit of a shortcut. So what I mean is if you've got a parameterization of the surface, let's say R, then we know already that RU cross RV is normal to that surface because each of RU and RV run in the direction of the U lines and V lines, which make both RU and RV tangent to the surface. So this is a normal vector to the surface. It's just not unit, right? So if I divide by its magnitude, I create a unit normal. And, there's sort of what I want to say is when you're going to decide on which direction you want your normals to point, it's all completely controlled in your parameterization. So like if you decide on a parameterization and you construct this normal, it's going to point to one side of the surface, assuming it's orientable, right? If you want to switch that up, one easy way to do it is to switch the roles of U and V. When you cross two vectors in the opposite direction, you know that it just points in the other direction according to the right-hand rule, right? So your control on the normal vector and which side it points is completely controlled with the parameterization. Okay, so this is how I could get a normal to put in this formula, but remember your ds, your differential form for the surface area, includes exactly that expression. So when you put a normal computed in this way next to the ds, the magnitude of RU cross RV vanishes. So we get a much better way of computing the flux integral with that observation. Okay, so if you have a parameterization of the surface, then just integrate this instead. Okay, so when you're computing this type of surface integral of a vector field, just like with all surface integrals, the first thing you do is parameterize the surface. Once you have that done, this flux integral just ends up looking like this. And this is actually very familiar because when we were talking about circulation in previous sections, we had developed this line integral of a vector field across a curve, and the circulation or work done was the amount of F that was running in the direction of the tangent vector across the curve. But we never really computed the tangent vector, right? Instead, we would just come up with a parameterization of the curve and compute the following. So you can really see, maybe if I zoom out, the similarity between what's happening here. We've got our notions of line integrals with respect to arc length, and we use them sometimes to compute something about a vector field along that curve, in this case the circulation of the field along the curve. I should say flow of circulation is used when this is a closed curve, but anyway, I might want to compute that, but through a parameterization, I get this sort of expression to compute the integrand. It's the same thing here. If I have a notion of surface integrals of various integrand functions across surfaces. And if I have a parameterization of that surface, then I can construct that integrand using the parameterization like this. So D here is the parameter space of U and V that is tracing out the surface S through the parameterization. Okay, so why don't we practice with this? Let's start with a vector field, 0, 0, x, and start with a surface, and they've kindly parameterized the surface for me, so there's going to be a direction imposed by this parameterization. I'll say more about that when I graph these things in Grapher, but let's just go ahead and try and work out the math. So I've got my parameterization. I know I'm going to need an RU cross RV, so let me go ahead and crank that out. Okay, and instead of going through and computing the normal from scratch by taking this divided by its magnitude, I know that that would be a waste of time because in order to get the ds, I'd have to multiply by the magnitude of RU cross RV. So I'm going to leave it at this, and then I'll go ahead and set up the integral. So my parameterization has U ranging from 0 to 1 and V ranging from 0 to 1. So that's the parameter space D. And then I'm going to take my vector field and evaluate it at the parameterization. So the vector field is 0, 0 times the x component. The x component here, where is it? Is given by U squared. So that is evaluating the vector field at the parameterization. And I dot that with RU cross RV. Okay, and at this point I'll have a double integral to compute. Okay, nothing difficult about this. This ends up being a half in the end. Let's go ahead and get a visual of what we just computed. Okay, so I plugged in the parameterization that I was given, and I get a surface that looks like this, right? So it's kind of got a top side and a bottom side, if you will. And I can think about the normal that's imposed by this parameterization, like which of the sides does it point to, by looking at the relationship between the U and the X and the V and the Y carefully. So like as U increases, I see that X increases along with it, right? So if I was to look at any U line, it would be running sort of parallel to the x-axis. As x increases, the u increases. And similarly, with the y variable, y is directly equal to v, so as v increases, the y increases. So the v curves are going to run in the direction parallel to the y-axis. So that tells me that when I take something like RU cross RV for this parameterization, I'm going to get something pointing out in the direction of the x-axis for RU cross something pointing out in the direction of the y-axis for RV, and according to the right-hand rule, that's going to make the normals go upward. So I can deduce all of that from the parameterization that was given to me. Sometimes you want to arrange that a parameterization points to one side. But this, like I said, this one was given. If I wanted the normals to point in the other direction, I would simply reverse the roles of U and V, and that would get it done for me. I've also graphed the vector field here. So this is how to graph the vector field 0, 0, x in Grapher. And as you can see here, it's a little bit clumsy, but it appears that the flow near the surface is going up through the surface. The flow vectors don't appear to be perpendicular to the surface, right? But they are passing upwards. So a certain amount of, like the components of those vectors that are running exactly perpendicular to the surface is what's captured by the flux integral. But at least with this image, I'm not surprised that I got a positive answer, because like the net amount of the field that is crossing from below to above appears to be positive. If you like reparameterize the curve so that it produced a normal that pointed downward and computed the exact same flux integral, it would be giving you a negative answer because it's detecting that there's a negative amount of flow that goes from top to bottom. That's the same thing as saying there's a positive amount of flow that goes from bottom to top. Okay, so that just kind of gives us a visual of what we're actually computing here when we're computing the flux of a vector field.